All right. Whoops. This Zoom session is being brought to you by the Fractal Globe Snow Ring B. All right. Now, okay. Last time we finished chapter 6. I'm skipping chapter 7 till perhaps later. If we don't get to it by the end of the semester, then consider it an extra credit set. But okay, so I think that chapter 8 is actually a little bit more relevant to people's general mathematical needs. So that's why I'm covering it. So today, 8.1 sequences and 8.2 arithmetic sequences. And I'm going into this because, among other things, later in this chapter, we briefly touch on the mathematics of mortgages and amortization, and that is very much a practical issue. Believe me, you need to know about that stuff before the credit people eat you. But I proceed. A sequence. All right. A sequence. A sequence is a list of numbers: A1, A2, A3, A4, AN, going on endlessly. So that for every integer whole number n, there's a sequence element A sub n. These are subscripts. All right. A1 is the first term, AN is the nth term. And yes, that word nth, NTH, is actually in the dictionary. I looked it up. It's one of the few words there are with no vowels. All right, now, sometimes we have a sequence defined by a formula. For example, AN equals 3n plus 2. If you plug in, so A1 is 5, A2 is 8, A3 is 11, A8 is 26, and so on endlessly. Just substitute the number n and you calculate it out. Here's a sequence 5 to the n. So B1 is 5 to the first, or 5. B2 is 5 to the second, or 125. B3 is 5 to the third, or 125. And so on. B8 is, let's see, 390,625, and so on endlessly. Okay. Now that's formulas defined by what are called closed formulas. Here it is, all it is before you. There are also sequences that are defined recursively. We don't have a specific formula for any particular number, but we can generate each element of the sequence. For example, here's a sequence where A1 equals 1. That's the initial condition. And for any n, an is twice a to the n minus 1 plus 1. That's the recursion. The idea is you start with A1 equals 1. And to find the next one, you plug in the previous value and calculate the next value. So A2 is twice A1 plus 1, which is twice 1 plus 1, which is 3. A3, twice A2 plus 1, so twice 3 plus 1, which is 7. A4 is twice 7 plus 1, which is 15. A5 is twice 15 plus 1, which is 31, and so on. Now, okay, sometimes these sequences, you can find a closed formula for the sequence. Sometimes it's a lot harder. Here's a famous one, the Fibonacci sequence. It starts with a 1 and a 1, and every subsequent entry is the sum of the previous two. So AN is AN minus 1 plus AN minus 2. So for example, here we add 1 and 1 and get 2. And we add 1 and 2 and get 3. We add 2 and 3 and get 5. 3 and 5 makes 8. 5 and 8 makes 13, and so on. Now, okay, it turns out this has a closed formula. It involves the number 5, which is an irrational number, the golden mean. Kind of curious that it should show up in this perfectly rational sequence. Or here's another one. P naught equals 5,000. Pn equals 1.08, Pn minus 1 minus 300. The idea is that at each step, think of it as an amount of money, which grows by 8% compound interest, but you withdraw $300 every month, well, every year, what have you. So this is 5,000 becomes 5,100, becomes 5,208, which becomes 5,234.64, and so on and so on and so on. By 11, it's 6,664.55 approximately. All right. Now, if you have a sequence, then you can create what are called its partial sums. A1 is S1, sum 1. A1 plus A2 is S2. A1 plus A2 plus A3 is S3. A1 plus A2 plus A3 plus A4 is S4, and so on. So you can take sums of finite parts of the sequence. Sn is denoted given this notation called sigma notation. sigma from k equals 1 to n of ak. So it's a1 plus a2 plus a3 all the way up to an. The sigma is a capital Greek letter sigma denoting sum. So, example, summation from k equals 1 to 4 of k is 1 plus 2 plus 3 plus 4 is 10. The sum from k equals 1 to 6 of 1 over k is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6, which after you calculate it out is 49 over 20. Some factors must have canceled. Here's a sum from 1 to 10 of k squared. 1 plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared, summing up to 385. Okay, well, this is notation. And you'll certainly, when you get to statistics, you'll see summation notation all the time, simply because it enables you to write in a few symbols what you would have to cover the page with long sums and maybe a dot, dot, dot in the middle. Hardly fun. So there's that for that.